Hello dear students. Let us understand concept of Moore and Mealy machines from this video onwards. I have written few definitions and differences between Moore and Mealy machine, and also I have shown examples of Moore and Mealy machines and their execution. But then before we read these definitions, let us understand on an empty slate what is basically Moore and Mealy machines. After that, we'll read definitions. Now, we have been learning finite state machines. Of course, the machines which have finite number of states. Now, we have learned DFA, deterministic finite automata, NFA, non-deterministic finite automata, NFA with epsilon moves, we have learned, correct? Now, all these are finite state machines. But the basic thing about these machines is that these machines take some input and they only tell whether the input is accepted or not accepted, whether that input string is in the language or not. So let us say that we define a DFA which accepts the strings of the form A star B, let's say. That means the strings which have the last character as B and only one B is allowed. But before that last B, there can be arbitrary number, 0 or more A's, correct? Now we can give any string to this. For example, if we give A, B, A, B, now notice this string will be rejected, isn't it? Because now the string contains B, agreed, but after B, A is not allowed. A is not allowed after B because there can be only one B and that too at the end. But what if we give A, B? Now this string which contains three A's and one B will be accepted. Now absolutely same work is done by NFA and NFA with epsilon moves. So all these three categories of finite state machines do not give any output. This is no output machine. Why? Because given a string, they will only tell whether the string is part of this language or not, A star B. That's it. They will either accept or reject the string. But such machines do not give any output. Now there is second category of finite state machines, FSMs. They are Moore machines and Mealy machines. Now, both these machines are basically finite state machines. That means they will have finite number of states like Q0, Q1, Q2, and so on. And these machines will give output. Given input string, given some input string, these machines will produce output. Okay. Now, one more characteristic of Moore and Mealy machine is that these machines do not have any final state. Recall in all the previous machines which either accept or reject the input, these machines were characterized by final or accepting states, isn't it? We used to double circle them. And given a DFA or NFA or NFA with epsilon moves, there can be one or more than one accepting state. There can be multiple accepting states, isn't it? We have seen that. But these machines, Moore and Mealy machines, are not supposed to accept or reject something. They are simply supposed to take some input and provide some output. Then such machines do not, both machines, Moore and Mealy machines, do not have final states. That is, accepting states are not there. Of course, these machines have initial state. And you know, any FSM can have only one initial state from where the machine starts. Okay. So what is the basic difference between the FSMs that we were learning till now and these two FSMs, Moore and Mealy machine, is that they will produce output. Many times these two machines are also called as transducers. Transducer. the basic definition of transducer is, given a transducer, you give some input, okay? For example, AABB. And this transducer will transform this input into output such that the output may be 1122. So every A is transformed to output 1 and every B is transformed to output 2. Just an example I am giving. So this is simple input to output mapping, which actually these transducers do. And same thing is going to be done by Moore and Mealy machines. Now let's see how these Moore and Mealy machines look like and how they produce output. One basic difference between Moore and Mealy machine, basic difference is both produce output. Obviously, both produce output, but in Moore machines, the output generated output is decided. Output is decided only by current state. Current state. Give me some time, you will understand what I'm talking about. Whereas in Mealy machine, the output is decided not only by current state, but it is decided by current state and current input. This is the only difference. Check. This is the only difference between these two machines. Otherwise, working wise and development wise, both machines are same. Now, what is this difference exactly? Let's try to understand. I'm drawing a Moore machine. I know this is too early because we have not yet read these definitions. Okay. But trust me, once we learn this, we will be easily knowing what those definitions are. Now I'm drawing something I am drawing. Even I don't know what I am drawing, but definitely it will be a valid Moore machine. Okay. So give me some time. Like suppose I have some machine like this. Just say that this is Q2 state and slash A I have written, and then there is a transition over here on 1 and there is a transition on 0 here. Okay. So this is a Moore machine. Moore machine. Just check out that this looks like DFA, isn't it? That means in this machine, sigma, the input symbols are 0, 1. Observe, because the transitions are labeled with 1 or zeros. Whereas the output symbols, the output produced by this Moore machine is going to be A, B. Just check. These output symbols, are written with the states. Like you will see Q0 slash A or Q1 slash B or Q2 slash A. These are basically the outputs produced by the Moore machine. And we can show it as a set. Like we are showing set of input symbols, these are set of output symbols. And let's use the Greek letter, okay, to show the output symbols. Otherwise, Moore machine is nothing but FSM, obviously. Note one more thing, there is no final state, no double circled ellipse, but there is initial state, obviously. Now, very quickly, you see the working of this Moore machine. No wonder you might be thinking, why is this Moore machine developed? Forget it. I have drawn some arbitrary Moore machine. Now, let's give some input like this 0, 1. This is the input given. Note, this is the input made up of 0, 1. Now, obviously, you will say that machine starts in Q0 state, correct? Machine has started in Q0 state and machine has not even read first letter of the input. But obviously, machine will be in Q0 state. What do you say, isn't it? Machine starts from here. As soon as machine enters Q0 state, the output is produced A. Just check. If the machine enters Q0 state, output is produced. Output labeled with Q0 is A. So we are telling Moore machine, if you are in Q0 state, print A or produce the output A. And now, after producing output A, Q0 is going to read this 0, the first input. Of course, the first letter will be always read by the initial state. Now, what do you see? What is the transition? What Q0 does on reading A? It is clear that there is a loop here. Q0 on reading a 0 On reading a 0, Q0 remains in the same state. That means machine was in Q0 and machine again enters Q0. Check, machine again enters Q0. And what does machine do after entering Q0? It prints A. Whenever machine will enter Q0 state, it will output A. Now what? Machine now reads 1. And of course, we are in Q0 state. Still we are in Q0 state. So Q0 will read 1. And what is Q0 doing on reading 1? Yes, it is going to Q1 state. Correct? So machine now is in Q1 state. But look, machine has entered Q1 state, so it will immediately output B. I hope you are understanding. After that, remember machine is in Q1 state now and it has just now printed B. After that, machine says the input is over. You can see that after 1, there is no input symbol remaining. So machine stops. There is nothing called accepting state, double circle over here. But the point is that the input given, observe, was 0, 1. Input given was 0, 1 and output produced is double AB. One thing you make an observation, very early you make this observation. If the input contains 2 letters, then the output surely contains 3 letters in the case of Moore machine. Again, if the input contains n letters, then the output contains n plus 1 letters, always in Moore machine. I'll tell you this first output, first output, A, was produced even before reading the first symbol 0. Because as soon as machine entered Q0 state, it printed A. And then it read the first symbol. So this, the very first output, is many times called as extraneous output, which is in fact not needed. But Moore machine is developed like this, that as soon as it enters a state, it will display or it will output the symbol. Okay, let's see one more example with the same diagram so that it is understood how this Moore machine is displaying or is giving the output. Here we go. Suppose I give some arbitrary input 1, 0, 1. Let's say this is the input. Input is made up of zeros and ones. Now, machine starts in Q0. Look, as soon as it enters Q0, it will output A. It has not even read the first letter. First letter 1 is not even read, but machine is in Q0, so it will output A. Now, in the Q0 state, machine is reading 1. The first input machine is reading. And after reading 1, Q0 goes to Q1. So in Q1, once the machine is in Q1, it will produce B. Now machine is in Q1 state, remember, and machine will read the second symbol 0. Yes, in the input, second symbol is 0. So Q1 is reading 0. Check the transition. On reading 0, machine goes to Q2. But as soon as machine is in Q2, it will produce output A. Just note that output produced is A. And now the machine reads 1, the third symbol of the input. Remember, the machine is in Q2 state. But after reading 1, Q2 transits to Q0. And if the machine is in Q0, it will output A. But now the input is finished, you observe, and machine halts. We are not bothered about machine halts in which state, because there is no final state. But the important thing is that the input given was 101, not 3-letter string, and the output produced was 4-letter string. Isn't it so? This A was produced right in the beginning. When the machine entered Q0, it outputted A and then it read the first one and then transited to Q1 and so on. So this is a very important property. You can see how the input is transduced to some output, isn't it? This is Moore machine. Now, as an example, if I draw Mealy machine, even Mealy machines will produce outputs. Mealy machine. Let's take an example of Mealy machine. Let's say Q0 reading 0 will produce A. Reading 1 will go to Q1 but produce B. Reading 1 will produce, let's say, B. Reading 0, okay, will produce A and go to Q2. and Q2 on reading 1 will produce A, and on reading 0 will produce A. Just check this. Just check this machine, and please try to understand sigma here, that the input symbols are again 0 comma 1. That means the input given to this machine will be made up of zeros and ones, but the output symbols are A comma B. Let's call it with a Greek symbol. These are the output symbols, and you notice that the output symbols are written on the transition along with the input symbol slash. Output symbols are written on the transitions. They are not written inside the states. That means in Moore machine only the state decides what is the output. Just ask in which state you are. Okay, I am in Q1, then output is B. In which state I am? Q2, then output is A. But in Mealy machine, the output is not decided only by the state. The output is decided by in which state you are and what is the input that state is reading. Let's take an example. Suppose I give the input 0, 1 again. So machine starts in Q0. Now you tell me, if machine is in Q0 state, if the machine is in Q0 state, there is no output yet produced, because only state will not decide the output. So in Q0 state, machine will read 0. But on reading 0, you can see that on reading 0, machine remains in Q0 state, but importantly produces the output A. The output A is produced when Q0 reads a 0. So the output produced is A. Okay. But then machine is still in Q0 state. So Q0 is now reading 1, the next input. On reading 1, Q0 will traverse to Q1, but on reading 1, machine will produce output B. So output produced is B. Remember, the machine is in Q1 state now, but after that the input is finished, you observe. So Mealy machine halts by giving the output AB. Note that input was 0, 1, had 2 letters, and output exactly has 2 letters. This is the basic difference between Mealy and Moore machine. In Mealy machine, if the input has n letters, then the output has exactly n letters. Whereas in Moore machine, you observe, if the input has 3 letters, then the output will be 4 letters. Okay, let's try this Mealy machine again with some input. Give me some time, I will just erase a few things. So let's try some other input. Let's try 101. How will this machine work? 101. Okay, machine starts in Q0, correct? But no output produced yet in Q0. So machine in Q0 reads 1. On reading 1, machine will traverse to Q1, but will produce output B. Observe, 1 slash B is written. So output produced till now is B. And the state? Yes, the state is Q1. We are now in Q1 state. In Q1 state, machine will read 0. On reading 0, machine will traverse to Q2, but the output produced is A on reading a 0. And machine is in Q2. Remember, now the machine is in Q2 state. In Q2, machine will read 1. On reading 1, it goes to Q0, but importantly, on reading 1, it produces output A. And now you observe that the input is over. If the input is over, machine halts, producing the output BAA. You note the input was 3 letters, 101, and the output is 3 letters. By the way, Moore and Mealy machines, are same, are alike, only with the basic difference about how they produce output. Just check, I have written this difference over here, that in Moore machine, output is decided only by current state, whereas in Mealy machine, output is decided by current state and current input. So let's go to the definitions. Nothing more to read now. See, Moore machines, it is FSM, finite state machine again, whose output depends only on the current state. Whereas in Mealy machine, it is an FSM whose output depends on both current input and current state. That's why, the output is written on the transition in Mealy machine. Whereas in Moore machine, outputs are written inside the state. Next thing is, how do you define Moore machine? Note that it is a 6 tuple. You recall q was set of states, sigma was set of input symbols. Now this Greek symbol, I call it as tau. I don't know what is this Greek symbol, please excuse me for that, but this is set of output symbols. Then delta is the transition function and lambda is the output function. Q0 is the initial state. All this description has been written over here. Most importantly, the transition function is same as transition function of any FSM or DFA. It is Q cross sigma maps to Q. That means in some state you are reading some input and you will go to some state. Whereas output function differs. Okay. But then before that, you see definition of Mealy machine. Now, Mealy machine is also defined as six tuple. Q is set of states. Sigma is set of input symbols. Don't worry, I'm going to run this actually in this video only for our examples. But this Greek symbol is the output symbols. Delta is the transition function. And lambda is the output function. Q0 is the initial state. You can see all this description has been written here. If you match this left hand side and right hand side, everything is same. Even the transition function you see is same. The only difference is how they produce output. The lambda function differs. This lambda function differs. You see this? Tell me, in Moore machine, who decides the output? Yes, the state Q decides the output. Remember, this Greek symbol is output symbol. Tell me, in Mealy machine, how is the output decided? It is decided on the basis of current state and current input, both. Decide the output, isn't it? That's the only difference. Let's go back to our example of Moore machine and Mealy machine. Okay, this was the Moore machine where the output is decided only by the current state. Just give me some time again. I'll make some room to write our observations. What are your observations here? What is this Moore machine? This Moore machine contains Q, sigma, correct? This Greek symbol, delta, lambda, and Q0. So what is Q? Set of states, Q0, Q1, Q2, three states. What is sigma? What is input made up of? Input is made up of 0, 1. That's evident on the transition we have written on 1, go to some state, on 0, go to some state. Okay, what is the output symbol? Clearly, output symbols are A, B. Now, notice output symbols have been written inside the states in Moore machine. What is delta? Interestingly, delta is always drawn as a table, isn't it? Recall. And the input symbols are 0, 1, and the states are Q0, Q1, Q2. Okay, but just manage this. Three states, and Q0 is the initial state. Notice no asterisk symbol here on any states. Asterisk symbols were drawn only for final states or accepting states. But Moore machine does not have any accepting state. Okay, watch the diagram. Q0 on 0 goes to Q0 itself. Watch it, watch it. Q0 on 0. There is a loop here. Watch this loop. Q0 on 1 goes to Q1. Q1 on 0 goes to Q2. Q1 on 1 goes to Q1, and Q2 on 0 remains in Q2, but Q2 on 1 goes to Q0. Tell me, isn't this same as any transition table that we used to draw for FSM? That's why delta is Q cross sigma. This is Q cross sigma maps to Q. Okay. Now, what is lambda over here? Lambda is the output function, I said, isn't it? What is lambda? Now, lambda is easily drawn like this. You see, I will make space here. We will say lambda is defined as follows. Lambda of Q0, because the output is decided only by state, is A. That means we are saying whenever the machine is in Q0 state, it will produce A. So lambda of Q1 is B, and lambda of Q2 is A. Isn't it so? And last element in this definition is Q0. Q0 is the initial state. What do you say? Isn't it so? Now let's come to Mealy machine. Okay, can we write these observations, definitions over here? So I'll just scroll down a bit. Okay, okay, what is Q? Q is Q0, Q1, Q2, correct? Okay, what is the input symbol? Sigma. Clearly, sigma is 0, comma 1. Input is made up of 0, 1. What is this Greek symbol? This is output symbol. Output is A, comma B. Okay, what is delta? I'll draw delta here. Delta is a table of Q cross sigma. Remember, sigma is 0, 1, and the states are Q0, Q1, Q2. Just check. Q0 on 0 remains in Q0, but Q0 on 1 goes to Q1. Check the diagram. Q1 on reading 0 goes to Q2, but Q1 on reading 1 remains in Q1. And Q2 on reading 0 remains in Q2, but Q2 on reading 1 goes to Q0. This is the same transition table that we used to draw for DFA, NFA, NFA with epsilon moves. So transition is not differing over here. What is different is the output. How do you show the output here? That's interesting, isn't it so? So I will make some place again over here. Okay, let's show the output. Now output here depends on the state and the input will decide the output. So the output is shown in the form of a table again. This output function lambda is shown as a table, and the input that we have is 0, 1, and the states we have is Q0, Q1, Q2, Q0 being the initial state. Okay, now remember, we are not talking about transitions, we are talking about output. Just refer the diagram and ask yourselves, what does Q0 produce when it reads 0? That means we are questioning lambda Q0 comma 0. What does Q0 produce as output when it reads 0? Check the diagram. Q0 produces A. Are you observing it? I'll change the color. See, Q0 on reading a 0 goes to Q0, but we are not questioning where does it transit. In lambda function, we are saying that when Q0 reads a 0, it produces A. I hope you are understanding. So in this table, we will say when Q0 reads 0, it produces A. When Q0 reads 1, it produces B. You observe, when Q0 reads 1, 1, it goes to Q1, fine, but it produces B. Similarly, when Q1 reads 0, it produces A, and when it reads 1, it produces B. Observe. When Q1 reads 1, it produces B. When it reads 0, it produces A. Finally, Q2 reading 0 produces A, and reading 1 produces B. This is the output function. And what about the last entity in the definition? Last entity is, of course, Q0, which is initial state. So the only difference is how these two machines produce output. That's it. Okay. By the way, coming back to our definitions, I hope you have understood this. Don't worry, we will be repeating these definitions every now and then when we come to our next videos on Moore and Mealy machines and actually construct some Moore and Mealy machines. Okay, have you gone through this definition? If the input string has n symbols, then Moore machine produces n plus 1 symbols. Whereas if input string has n symbols, then Mealy machine produces n symbols. Okay, have you gone through this? These were the pictures that we have drawn on the empty slate. Okay, so see you in the next video with more concept on Moore and Mealy machines. Thank you very much.